So here we can see that we have 5 grams of impure magnesium carbonate, and this is added to 9.033 exponent 22 molecules of hydrochloric acid. Okay. The balanced equation for the reaction is given. So we have 1 mole of magnesium carbonate reacting with 2 moles of hydrochloric acid in order to produce 1 mole of magnesium chloride, 1 mole of carbon dioxide, and of course, 1 mole of water. And we now understand that this 5 grams is impure. It doesn't mean it's 5 grams of magnesium carbonate. No. It means magnesium carbonate is there in a total sample having a mass of 5 grams. Or rather, in a sample having a total mass of 5 grams. That's what I should have said. Nevertheless, the reaction is allowed to proceed until all the pure magnesium carbonate completely reacts. In other words, magnesium carbonate is the limiting reagent. Oh, they also give you something else. They say the excess hydrochloric acid is neutralized by adding 55 cubic centimeters of sodium hydroxide solution having a concentration of 0.8 mole per cubic decimeter. And this is the balanced equation for the neutralization of the acid, which is nice. Everything is in a mole ratio of 1:1 there. That's fine. Okay. So now the first question says we need to calculate the initial number of moles of the hydrochloric acid. And when we look at this situation, we have dealt with this before, at least one example on it, and we called it a back titration. So how do we get the initial moles? By initial moles, we mean the available number of moles at the start of the reaction. So, well, we are going to use the number of molecules which is given to us because we have learned about a formula which we apply when we want to find the number of moles given the number of molecules. So it's the one that they taught you in grade 10, but we did a little bit of revision on it when we began our quantitative aspects. So we'll say, well, the number of moles of hydrochloric acid which are available at the start of the reaction is equal to the number of particles divided by Avogadro's number. And you also remember when I told you that this N in the numerator, it is for particles. And by particles, we mean atoms or molecules, even ions. So it's a general one. So in this case, it means molecules. It's not specific to the number of atoms. So, well, the number of molecules is 9.033 exponent 22. And Avogadro's number, hey, I think it's 6.02 times 10 to the power 23. Yes, I think so. If it's not, please correct me because I don't have my table of constants. I'm just trying to get it from my memory. So when we go to the calculator and say 9.033 times 10 to the 22 divided by 6.02 times 10 to the 23, well, we get 0.15, 0049, and so forth. Well, this one, it makes perfect sense for us to take it to 2 decimal places. Perfect sense. We have 2 zeros after the 1-5. So they won't really have that much of an impact. Of course, the impact will be there, but it won't be that great. So these are the moles of hydrochloric acid which are available at the start of the reaction. And for this one, I'm not going to ask you if you have a question on it. So let's move on to the next one. Oh, I think what I wrote here is now giving me a challenge. So what can I do? Yes, the next question is asking us to calculate the percentage purity of magnesium carbonate. In other words, how much magnesium carbonate is there in this impure sample having a mass of 5 grams? But of course, we express it as a percentage. And this is actually for 8 marks, right? So the question is, how can we find this? We just need to know what is the mass that is present in these 5 grams. And how can we find the mass of magnesium carbonate? Well, that's if and only if we know the number of moles of magnesium carbonate. Now the question is, how can we find the number of moles of magnesium carbonate? Well, we can find them by actually finding the number of moles of the acid that reacted with magnesium carbonate. I hope you get what I'm saying to you. We already calculated the number of moles that were there at the start of the reaction, but we know that we can use sodium hydroxide in order to calculate the moles in excess, because they tell us that the excess acid is neutralized by sodium hydroxide. So let's begin by doing that actually. So, well, we need to find the number of moles for sodium hydroxide, but we know that we are given the concentration as well as the volume. So we need to define the concentration of the sodium hydroxide solution. Well, we know that it's defined as the number of moles divided by the volume. So that's what we say. And the concentration here is 0.8. The number of moles is N. And the volume, well, it's given to us in cubic centimeters. So we need to divide it with 1,000 in order to take it to cubic decimeters. And when we do, we properly get 0.055. Now we can conclude and say, well, the number of moles of the base will simply be what? We cross multiply here. And after we successfully do that, well, these are the number of moles of the base that we get. But then if you look at your second reaction, you can see that sodium hydroxide and the acid, they actually react in a 1:1 ratio, which means that the number of moles of the acid will be exactly equal to the number of moles of the base. Equal amounts are needed in this case in order for the acid to be neutralized. So now that we know the moles of the acid that are in excess, very important, then we can find those that reacted with magnesium carbonate by using our famous formula that says the number of moles in excess is equal to those that were available at the start minus those that are needed or those that are used to react with magnesium carbonate. Well, we are mathematicians here, and we know that if you want to make this the subject, you just take it to the left-hand side and you take those in excess to the right. So in other words, the number of moles that were used or that were needed or that reacted with magnesium carbonate will simply be 0.15, which is available, minus in excess 0.044. And of course, when you say 0.15 minus this, we find that 0.106 moles were actually used to react with magnesium carbonate. But listen to what I'm saying to you. I'm saying 0.106 moles of the acid were used to react with magnesium carbonate. That is not the same as saying 0.106 moles of magnesium carbonate were used to react with the acid. No, these are still the moles of the acid alone. And looking at the balanced equation between magnesium as well as magnesium carbonate and the acid, we can see that the mole ratio is 2:1. So magnesium carbonate is to hydrochloric acid. Well, it's actually 1:2, yes? So 1 mole of the base for 2 moles of the acid. So now we want to know if 0.16 moles of the acid is needed to react with the base, then how much of the base do we need? Well, of course, you now understand that you need to divide this by 2 and times it by 1, which would mean that the number of moles of the base will simply be, well, if we divide this by 2, we get 0.053, and then we say moles. Okay. So now we know the moles of the base. It's now easy to find the mass of the base. So we know that the number of moles are actually defined as the mass divided by the molar mass. Well, we have 0.053, which is set equal to mass there. And what is the molar mass of this magnesium carbonate? Well, magnesium has a molar mass of 24, carbon 12, and then 3 oxygen atoms, each with a mass of what? 16. So when you add everything up, you get 84. Then you times it by 0.053, in which case you get 4.452 grams. Okay. So now we know the mass of this metal carbonate. We can now easily go to the percentage purity. So we know that it's going to be the mass of our metal carbonate divided by the mass of the entire sample, the impure sample. And we times this by 100. Then when you press your nice calculator, you get 89.04%. Hey, Van, when I say you destroyed it, more life to you, Sam.